Alright, we're going to give this a go. There's a number of things I want to show in this video. How to determine the expected value for a single draw given some kind of population proportion, how to derive the variance for that same random variable, and then looking at statistics that you would get from sampling a number of times from the random variable. Okay, how to get the expected value for the sample proportion given some number of draws, and how to get the variance for the sample proportion. And I'm going to do a special case where you're just doing 2 draws. Okay. So the expected value of this random variable is always just the sum of x, p of x. In our case, we have 0 times 0.6 plus 1 times 0.4 is equal to 0.4. And this is like mu of our random variable. And in this case, we can call it the population proportion. It's equal to the proportion in the overall population. Sorry, I meant to go through this. This is just like the idea if we're doing a sample on this, in this situation, it would be like drawing from this bag and seeing what you get. Okay. Just one draw from the bag. Knowing the proportion. So this is just theoretically what's going on. Okay, so that takes care of objective 1. Okay, then we want to get the variance of x. Well, we know that the variance, as we've seen in other videos, is just the expected value of x squared minus the expected value of x squared. In our case, this is going to be sum of x squared px minus, well, we already have computed what this is. The expected value of x is just p. So we can say that we're taking away p squared. Okay, getting on with this. This sum would just be 0 squared times 0.6 plus 1 squared times 0.4, which is just equal to 0.4. Generally, this is 1 minus p squared times 0 plus p equals p. Okay, so we've got our expected value of x squared just being equal to p, and we're taking away from that p squared. And a lot of this is the answer, but a lot of the time you'll see it formulated as p times 1 minus p. And a lot of the time, if you want to think about 2 parameters, even though there's only really one, you could call this thing q. So you could say that the variance of x is equal to pq, which is pretty easy to remember. Okay, very well. Let's move on to the expected value for the sample proportion. Okay, so now we're going to have a new random variable. And the way we want it to be distributed is as our sample values. So suppose we were going to just take like n samples, and then we're going to divide by the number that we had. So this is like kind of like it's a sample mean. And what do we expect of this? Well, the expected value of now our an even bigger x. You know what? I'm going to just call it y, because I think it's the thing to do. Oops. The expected value of y would then be the expected value of all of this stuff. Plus xn over n. and we would see that the n could come out, 1 over n will come out of the expected value, and then we're just left with the expected value of x1 plus expected value of x2 all the way up to xn. But we already know the distribution of these guys. We already know that each one of these is p. So we would end up with np over n, or simply p. Okay, so our expectation for this random variable is the same as for our sort of lower random variable on the hierarchy. And that goes to show that this is an unbiased estimator. Your sample mean is an unbiased estimator of the population proportion. Okay, good. Check, check, check. Next we want to get at the variance. Okay, and I'll do my special case here. Bear with me. This is the home stretch here. Okay, the variance of y is the variance of x1 plus x2, over 2. Okay, so this looks like a function of random variables to me. And since variance is defined based on expectation, we know how to deal with expected values for these functions of random variables. And the way we could say that this is equal to the expected value of x1 plus x2 over 2 squared minus the expected value of x1 plus x2 over 2, all of that squared. We already know that this is just p, so we have our p squared there. Now what happens over here is a bit trickier. We're going to square the 4 and get it out of there. So we're taking 1/4 the expected value of x1 plus x2 squared. Okay, let's just deal with what's inside the parentheses here. We have x1 squared plus 2x1 x2 plus x2 squared. And we need to take an expected value of all of that and divide it by 4. Okay, expected value is going to distribute across. We've already seen the expected value of x1 squared, right? It's the same as the expected value of x squared, which we've already calculated to just be p. So we get 2p out of this part, plus something else. Okay, well, plus 2 times something else. Okay, x1, x2. We know that since these are independent, sorry, I just need to show the thing up here. Since these are independent, the expected value of x1, x2 is just going to be the sum of all possible x1, x2s times their probability of both occurring, x1 and x2. Okay, well, possible pairings of x1, x2 would be 0, 1, 1, 0, 0, 0, and 1, 1. Now, when we multiply the x's, all of those are going to go away except for one of them, which is 1, 1. 1 times 1 is 1, and the probability of getting 1, 1 would just be p squared. Okay, so now we've got our what comes out of this expected value here is p squared. So we have this guy over 4 minus p squared. Okay, well, we know that those are going to want to cancel. The 2 will cancel the 4. So we would get p plus p squared over 2 minus p squared. Okay, so we can just multiply top and bottom by 2 here. And so what we're left with is, and this is the final answer, so we want to have a drum roll, please. What we get is p minus p squared over 2, which is equal to p times 1 minus p over 2. And as we derived earlier, the variance is p times 1 minus p, so it's just the variance over 2. So in our sample of size 2, the variance of the sample mean was the variance of the random variable from which we were drawing divided by 2. Okay? And in general, this is going to be good. So the variance will just be equal to sigma p over n. Oh, sorry. Sorry, everybody. Sigma x over n, where x represents the whatever is generating your random variable proportion. Okay, thank you very much.